Hi, my name is Matthew Kishe, and I major in electrical engineering at Florida State University.
And I'm Hallie Weitzman. I major in computer science at the University of Maryland at College Park. This short presentation covers the highlights of our research on feature mappings via periodic evolutions of diffeomorphisms. Many machine learning tasks involve the modeling of data distributions, which gives rise to probabilistic generative models. On the other hand, in typical data analytics scenarios, the available data seem to originate from arbitrary distributions that are, in general, difficult to model. This motivated us to develop a nonlinear model that could potentially yield more tractable or useful distributions for specific machine learning tasks, such as classification and clustering, just to name a few. Our work was inspired by the work of Bernard Schulkopf and Christian Walder, titled Diffeomorphic Dimensionality Reduction, that appeared sometime in 2008. Their model transforms the original data in a way that it reduces their dimensionality. As you can see here, the original samples that occupy part of the plane are eventually mapped close to the x-axis, which practically renders them unidimensional. So to explain some of the technicalities a little more, the term mapping simply means transforming data from one form to another through the use of a mathematical function. Some examples of linear mappings include reflection, rotation, and scaling. Our model is able to accomplish something similar, as we will show next, but with a different type of transformation, which at least in principle allows to be inverted. Given the image of a sample around the transformation, one can efficiently find this sample's original location. This is mainly due to the fact that the mapping is periodic.
So, what does this do? Simply, it attempts to yield a data distribution that can be described in simpler terms. A good example of a simple distribution would be a Gaussian distribution, because one only needs a mean vector and a covariance matrix to describe it. To better illustrate this idea, here's an example of how some data may look like in its original state. This is an arbitrary distribution which is hard to describe and, therefore, to model. However, after applying our transformation and finally mapping the samples, the data now appears as if they are sampled from a Bavaria Gaussian distribution. As mentioned earlier, such a distribution is simple to describe and can form the basis for several machine learning modeling approaches. We foresee that the results of our research will provide scientists the means of more effectively modeling their data, so that machine learning tasks such as classification exhibit improved performance. In our work, we documented such improvements on fingerprint classification problems, deciding whether tumors are malignant or benign, and a facial recognition task. Here are the results we've achieved for the fingerprint classification problem we considered. Utilizing the transformation, each class is well clustered. Also, for the facial recognition task, our model is able to determine the gender of the person based off face measurements with higher accuracy than other well-known classification approaches.